Welcome to Ask and Learn.
We are given a reversible reaction between two different sulfur allotropes, and we want to find the values for the change in enthalpy, delta H, and change in entropy, delta S, for this reaction in order to help us determine at what temperature this reaction comes to equilibrium. We can use these two equations in order to help us solve for delta H and delta S of reaction. For delta H, we find the total change in enthalpy of the products and then subtract the total change in enthalpy of the reactants. For delta S reaction, we find the total entropy of the products and then subtract the total entropy of the reactants. After we find both of those values, we can use this equation in order to find the temperature at which the reaction comes to equilibrium, since we know that at equilibrium, delta G is equal to 0, and we will have then solved for delta H and delta S. So that's the process that we are going to use to work through this problem. We begin by starting with finding delta H. We use this equation again in order to determine that, and we start with the total change in enthalpy of the products. And we see the only product of this reversible chemical reaction is S monoclinic. And so we have just a single mole of that, and we can look up in the appendix what the change in enthalpy of formation is for that substance. And when we multiply those together to cancel out moles and get total energy units of kilojoules for the total change in enthalpy of the products, we get 0.3 kilojoules. For the reactants, we just have 1 mole of sulfur rhombic. And when we look up the enthalpy of formation for that substance, we see that it is 0, meaning that the total change in enthalpy of the reactants is 0 kilojoules. So the total enthalpy change of the products minus that of the reactants is just equal to 0.3 kilojoules. And that corresponds to delta H for this reaction. And now we use this equation in the middle to solve for delta S reaction. Again, we have 1 mole of both reactant and product, and we look up the standard molar entropy of each one of these substances in the appendix, which has units of joules per mole Kelvin. And this time, when we cancel out the units of moles, we are left with total entropy units of joules per Kelvin. So we can get the total entropy of the products and then subtract the total entropy of the reactants to get the overall change in entropy of this reaction to be 0.7 joules per Kelvin. So now we have values for delta H reaction and delta S reaction. And now we can rearrange this equation in order to solve for the temperature when this reaction is at equilibrium, meaning when delta G is equal to 0. So when we rearrange that equation to solve for temperature, we get this expression, and recall that at equilibrium, delta G is equal to 0. So that's what we plug in for delta G, and we just solved for delta H and delta S. So we can plug in everything that we know now to solve for that temperature when delta G is equal to 0. So temperature equals delta G, which is 0 kilojoules at equilibrium. And then we subtract delta H, which we found to be 0.3 kilojoules. And then we divide by the negative of the entropy that we calculated, which was 0.7 joules per Kelvin. But we should convert this into kilojoules by dividing by 1,000. So that the units of kilojoules in the denominator cancels out with the units of kilojoules in the numerator, so that we are left with temperature units of Kelvin. And now when we solve that out, we should get a temperature for when this reaction equilibrates to be equal to about 429 Kelvin.